Today I will be talking about the binomial theorem. What is the binomial theorem? Consider x and y real numbers. Then we have x plus y squared equals x squared plus 2xy plus y squared. And we can even try this with something bigger, like x plus y cubed. And this would be x plus y times x plus y times x plus y. And we know x plus y squared equals x squared plus 2xy plus y squared. And this would just be times x plus y. And now we have x cubed plus 3x squared y plus 3xy squared plus y cubed. And what if we want to try something even bigger now, like x plus y to the 9th, or x plus y to the 101. Now clearly, these would take a very long time to expand. So our solution would be to use the binomial theorem to do this much quicker. So, the binomial theorem says that we have two real numbers, a and b, and for each n in the natural numbers union 0, we have that a plus b to n equals the sum of k equals 0 to n, and choose k, a to n minus k times b to the k. To make this a bit more concrete, let's consider if we had n equal 5, then a plus b to the 5th equals the sum of k equals 0 to 5. 5 choose k times a to the 5 minus k times b to the k, which is a to the 5th plus 5a to the 4th times b plus 10a cubed times b squared plus 10a squared times b cubed plus 5 times a times b to the 4th plus 5b to the 5th. And you'll notice that these coefficients look a bit familiar. And this comes from the 5 choose k, which is the 5th row of Pascal's triangle, where each k is a column in Pascal's triangle, and that's where our coefficients came from. So how would we prove this? We would need a proof by induction. And so basically, after we prove the base case, we'd have to prove that if p of n is true, then p of n plus 1 is true as well. So, let's have p of n be the statement a plus b to n equals the sum of k equals 0, then n choose k, a to n minus k, b to k. And if this is true, then p of n plus 1 is true, and p of n plus 1 is the statement a plus b to the n plus 1 equals the sum k equals 0 to n plus 1, n choose k times a to the n plus 1 minus k times b to k, and this would have to be true as well. So our next key idea would be to use Pascal's triangle recurrence relation, which is n choose k plus 1 equals n choose k plus n plus 1 choose k. We should also note that a plus b to n plus 1 equals a plus b to n times a plus b. And a plus b to n, we can use the inductive hypothesis on this. Using that, we have that the sum of k equals 0 to n, choose k, a to n minus k, b to k times a plus b. And distributing a plus b, we have the sum of k equals 0 to n choose k, a to n plus 1 minus k, a times b to k plus sum of k equals 0 to n choose k times a to n minus k times b to k plus 1. And from here, it kind of looks like the binomial theorem, and all we'd have to do is re-index the summations and do a bit of arithmetic. And in the end, we'll have that a plus b to n plus 1 equals the sum of k equals 0 to n plus 1, n plus 1 choose k, a to the n plus 1 minus k, b to the k. So it is true that if p of n is true, then p of n plus 1 is true as well, and we can conclude that p of n is true for all n in the natural numbers union 0. So let's do an application of this. If we want to find the size of the power set of a set S, we could actually use the binomial theorem to find this number. We have that n choose k is the number of subsets with k elements of S. And then we would have that the sum of k equals 0 to n choose k is the total number of subsets of a set with n elements. Going back to the binomial theorem, which is a plus b to n equals the sum of k equals 0 to n choose k, a to n minus k, b to k, we need to find an a and a b such that a to n minus k times b to k equals 1. And we find that if a equals 1 and b equals 1, it works. And often when we use binomial theorem to solve problems, we have to cleverly pick our a and b such that we get the numbers to match up on the left and right sides. So, using a equals 1 and b equals 1, we have 1 plus 1 to n equals the sum of k equals 0 to n choose k, 1 to n minus k times b 1 to k, which is 2 to n equals the sum of k equals 0 to n choose k. So let's try this with a set A, where the size of set A is 365. Then the power set of A, which is the set of all subsets of A, has a size of 2 to the 365. Thanks for watching.